It starts with benzene. Alright, let's continue with benzene. Electrophilic substitution. This is the main reactions for all the benzene molecules that we find anywhere. Now we know that benzene, right, has got 3 pi bonds, so it means that it is electron rich. But the thing is, it is less reactive due to the aromatic stabilization. We have the delocalization of electrons around the ring, round and round. Okay, so this does not act as a nucleophile. Unlike an ordinary alkene that's used to give out your pi electrons to an electrophile like Br2, you have an addition product. Here we do not see something like this going on. In fact, it will react to form a substitution product, because I would like to preserve the very stable aromaticity of the system. I try to regenerate this very stable. This is to illustrate equal bond length and electron delocalization around the ring. You can use your pen to denote that we have electron pushing mechanism here. We just get a pen. Pi electrons move to the neighbor, can be clockwise or counterclockwise. This got to give way, push and push. Think of it like a, like a funny house with door slamming and the other door must open, slam shut, open. Okay, it can't be closed all the time. Now what happens is, first the electron-rich benzene ring will use its electrons to attract an electrophile, which we call it E+. E forms a bond there. The next carbon must take a plus charge. But then in the next step, a base will come in and pick up this H that was attached to the carbon that has the E. So that now this bond here will break. The electrons here will go back to the ring and reform the aromaticity. So we call this re-aromatization, because you decrease in the energy of the system, yeah? These two are very similar. You can push this side first using electron pushing, and these are resonance structures. So here are some examples of what are the products you could get under different reagents. Now for an ordinary benzene, if you throw in some X2, X meaning halogens here, in particular chlorine and bromine, in the presence of a halogen carrier, iron-free halides, then X goes in and we call this halogenation. You get bromobenzene or chlorobenzene. The next step, you throw in concentrated sulfuric acid and nitric acid. You have nitration, NO2 goes in, kick out the H. And lastly, you throw in a fuming H2SO4, a very angry exasperated reagent here, and you are doing a sulfonation reaction. What happens in the first step is here, for chlorine and bromine, step 1, the halogen carrier, which is short of electrons, pick up the X here, okay, and forms a salt. This is a Lewis acid-base reaction and generate this X+, which is like an E+ electrophile. The second step, for the nitric acid, we have an acid-base reaction here. You form an intermediate and generate a nitronium ion. And for the fuming sulfuric acid, likewise, is similar to the second step. You see, we have another electrophile. So the first step is always to generate the electrophile. Here, our electrophile is the carboxyl ion. You see, what I told you guys before, right? Doping. You substitute something that's similar to the one before. In this case, you could see it's a whole entity. C on the right, C on the right. You throw in this Lewis acid, you will pick up the one on the right. Then you are left with the left hand side with a positive charge. So you see, you dope it inside. And after that, you place the benzene ring with it. It will just form a bond with this color in red. Very simple. We term this a Friedel-Crafts alkylation, because we put an alkyl group onto the benzene ring. For the next step, again, it's very similar. You practice doping. You see, here we throw in a Lewis acid, some halogen with some branch here. Doesn't matter what this is. You group this part together, then this bond will just join to the ring. We call this acylation because this is the acyl group. Now for alkylation, we have some limitations here because there could be some rearrangement that may occur to give undesirable products and a mixture of products. The reason is because when we first generate these, which is a primary carboxyl ion, it is not stable. So in chemistry, we have something called the hydride shift, where the H bond here adjacent to the positive charge will break and goes on to this C. That means they swap places. The H and the plus charge swap places. And you get a secondary carboxyl ion, which is much more stable compared to the primary carboxyl ion. Then now, your benzene will attack this, and voila, you see, we got a secondary butyl benzene. Of course, there may be some of the primary carboxyl ion present, and you can get a butyl benzene. So we have a mixture of products, not desirable, because sometimes it's very hard to separate these. For the second example at the bottom of this slide, you could also have a methyl shift. That means now instead, the alkyl group or the methyl group specifically will swap position with the positive charge to attain a more stable intermediate. From primary carboxyl ion, this whole bond breaks, goes over, you get a tertiary carboxyl ion, very stable. In this case, it's not even formed. The reason is because it's primary against tertiary, so this outweighs. This is so stable compared to this, so you don't get this at all, not formed. Let's compare some of the reactivity of substituted benzene. So this is what we call a naked benzene, which means it's not substituted. It's electron rich relatively, so it undergoes electrophilic substitution, not addition, substitution. Now here we have electron donating groups. These donating groups will push electrons into the ring, which makes the ring more electron rich and hence more susceptible to electrophilic substitution, right? And if we have W, which stands for electron withdrawing group, it will pull electron density away from the benzene and hence will make the molecule less electron rich and hence is less prone or make it slower to electrophilic substitution. So now let's look at this example here on the right side. Y is an algebra, we can change it. Now we are doing the next substitution using the nitration and we see the effect of the different substituents for Y. Naked benzene is 1. If you have an OH group, this is a phenol, 1000 times faster. Chlorine, much slower. If it's an NO2 group, it's so slow, very slow. So this is a scale, very important. You have to remember the relative positions of the substituents that will allow enhanced substitution or it will impede further substitution. Very important. You see how many stars I'm putting here? Extremely important. Same for this. This is again to explain to you why these groups on the left, they are called deactivating because they will hinder further substitution. On the right side is activating. They are electron donating. They will reinforce electron density towards the benzene, so making it more prone to electrophilic attack. Alkyl groups increase electron density by the effect called hyperconjugation. You have learned this in the previous lecture. The rest of them, you notice that the atom it is attached to the benzene ring has a lone pair of electrons. Let me emphasize to you that it doesn't matter how many lone pairs, as long as it's got one lone pair, that's good enough because the lone pair can overlap with the p orbital of the benzene ring and push some electron density towards it. Okay, and this is the resonance structure that it will form. Stable. You may see that oxygen and nitrogen, they have this electron withdrawing effect, right? But it is caused by inductive effect. Here is quite weak, so it's not so effective. The main trick here that they play is the very strong electron donating effect using resonance. For the halogens, they have lone pair, but they are not good electron pair donor, so they just pull electrons a bit. They are more of deactivating. You see, it's on this side. Now for all this, right, you will notice something in common. All of them we have a pi bond, except for the last one. This is the worst guy if we have a net positive charge. When we have a polarized pi bond, you see that right here, this delta positive charge atom is always beside the ring. When you have a neighbor that wants electrons, it will pull from you, it will ask from you, so it makes the ring less electron rich by resonance effect. For the last one, this is very special because there's no pi bond, so we can't do any electron arrow pushing. It is an inductive effect due to the net positive charge. This is the worst guy, the best deactivating group. To illustrate a bit further, what happens is, right, the lone pair adjacent to the ring can be pushed into the ring, and see the ring becomes net negative charge. That means the ring has achieved more electrons, and this is stable because we have a few resonance structure to showcase it and distribute the energy of the system. And similarly, for these electron withdrawing groups that are deactivating, we can push electrons out of the ring and still stabilize them, and you see that now it gains a positive charge. That means it's more electron deficient.